Good morning everyone. Today we will study countability. First of all, what is first countable space? A first countable space is a space in which there exists a countable local base at each of its point. Suppose X is a topological space. The space X is said to satisfy first axiom of countability if X has a countable local base at each point of X belonging to X. The space X in this case is called first countable or first axiom space. So first axiom space and first countable space is one and same thing. A first axiom space is a space in which there exists a countable local base at each of its point. For example, every discrete space is first countable space because every subset of X is open. In other words, singleton set X is open and contained in every open set G containing X, where X is a point of capital X. One more example is that every metric space is first countable space. Suppose Xt is a metric space and X is any point of X. If we consider a collection of balls centered at X and radius 1 upon n, where n is a natural number, we have denoted it by S, then if n is any neighborhood of X, then there exists epsilon greater than 0 such that the ball centered at X and radius epsilon is a subset of n. If we choose n to be so large that 1 upon n is less than epsilon, then the ball centered at X and radius 1 upon n is a subset of a ball centered at X and radius epsilon, and this is a subset of n. It means every neighborhood n of X contains a member of Bx. Member of Bx is a ball centered at X and radius 1 upon n. And therefore Bx is a local base at X. It means Bx is surely countable. Hence X is first countable, or we say that a metric space Xt is first countable space. The property of being first axiom space is a hereditary property. In other words, we say that the subspace Yt star of first countable space Xt is also first countable. Let Xt be a first countable space and let Yt star be a subspace of Xt. Now we will show that Yt star is first countable space. Let Y be arbitrary point of Y. Then Y belongs to X. Since Xt is first countable, there exists a countable T local base By at Y. Now it is easy to see that collection B star Y, which is nothing but Y intersection B, where B belongs to B star Y, form a T star local base at Y. T star is the topology on set Y. It means the set Yt star is also a first countable space, or we say that it is a first axiom space. So it means the subspace of a first countable space is also first countable, or first axiom space is a hereditary property. What is second countable space? A topological space Xt is said to be second countable if and only if there exists countable base for T. The space Ru, where R is set of real number, is second countable since the set of all open intervals AB, where A and B are rational numbers, form a countable base for U. And the space Rs, where S denotes the lower limit topology on R, is not second countable. The second countable space is first countable space, but the converse is not true. Let's prove it. Suppose xt be a second countable space and let B be a countable base for T. Let P be any arbitrary member of X. If BP is countable local base at P, it means xt is first countable. So we have shown that second countable space is first countable. But the converse of this result is not true. For example, every discrete space is first countable, but it is not second countable because there does not exist a countable open base for this space. Now one more result. Let xt be a second countable space and let A be an uncountable subset of X. Then some point of A is an accumulation point of A. Suppose B is equal to Bn, where n belongs to some indexing set which is a subset of natural numbers. Let B be countable base for T. And suppose if possible, no point of A is an accumulation point of A. We have assumed opposite. We need to prove that some point of A is an accumulation point of A. So we are supposing that if possible, no point of A is an accumulation point of A. Then for each x belonging to A, there exists an open neighborhood G of X such that G intersection A is equal to singleton set X. Since B is a base, we may choose a set Bnx which belongs to B, where Nx belongs to some indexing set such that X belongs to Bnx and this is a subset of G. Then from here, because G intersection A is X and X belongs to Bnx which is a subset of G, it means Bnx intersection A is singleton set X because it is a subset of G. Note that for each x belonging to A, we must get different Bnx such that Bnx intersection A is equal to X. For we have x not equal to y. If x is not equal to y, then singleton set x is not equal to singleton set y. And this is possible if and only if A intersection Bnx is not equal to A intersection Bny. And this is possible only if Bnx is not equal to Bny. So for x not equal to y, we have shown that Bnx is not equal to Bny, and this is true in both ways. Means if Bnx is not equal to Bny, then x is not equal to y. So there is a 1-1 correspondence between point of set A and member of subcollection of B. It means A is countable. But we have assumed that A is not countable. No, not assumed, it is given to us. It is given to us that A is an uncountable subset of X. But here we are saying that A is countable. So this is a contradiction to our hypothesis. Hence A must contain an accumulation point of itself. The product of second countable space is second countable. Let x and y be two second countable space. It means we have to prove that x cross y means product of x and y is also second countable. Suppose B star and C star be countable bases for x and y respectively. B star is a countable base for x and C star is a countable base for y. If we consider the collection D star of product B and C, where B belongs to B star and C belongs to C star, then D star is surely countable. Because if A and B are countable, then their product is also countable. Also, D star is a base for product topology. Means if xt and yv be two topological spaces. Here it is topological. If xt and yv be two topological spaces and b star is a base for t and c star is a base for v, then d star is a base for the product topology. It means D star is countable, D star has a base for the product topology. So x cross y means product of x and y is also second countable. So we have shown that the product of two second countable space is second countable. Now Lindelof space. A topological space xt is said to be Lindelof space if and only if every T open cover of X has countable subcover. It means by the definition of Lindelof space that every compact space is a Lindelof space, but the converse may not be true. For example, the space XD is a Lindelof space where X is any infinite countable set, but it is not compact. So it is not compact. So every compact space is a Lindelof space, but every Lindelof space may not be compact. Now the Lindelof theorem, every second countable space is a Lindelof space. It means every open cover of second axiom space or second countable space is reducible to a countable subcover. If xt is a second countable space and B is a countable local base for T, suppose C is an open cover of X. Then we want to show that C has countable subcover. Now each member of C is expressible as a union of members of B. Let D be the collection of all those members of B which are actually required for expressing members of C as union of members of B. Then D is countable, being subcollection of the countable base B. Hence D is countable open cover of X. It means for each Di belonging to D, we choose a Ci belonging to T, C such that Di belongs to Ci. Hence, the collection of these Ci's is also countable open cover of X. In other words, C has countable subcover. Thank you.